So I'm going to give a proof of the theorem that we would call the Pythagorean theorem. That's probably not what the people who gave this proof that I'm about to give called it. Left my markers again. I'm going to give, so the book goes over two different arguments. I'm going to give the one that I've seen before. I actually have a friend from grad school that basically had this image tattooed on his leg. Anyways, this is the argument by Zhao Shuang. Okay, and it's a diagram. It goes like this. So let me just explain everything. Maybe some of the green is not showing up as nicely as I wanted to, but I really need three different colors here. So this is H. The idea is that we start with a right triangle whose this side length is A. That's the shorter side length, and then B is a longer side length, and H is the hypotenuse. So of course the goal is we want to prove that A squared plus B squared is equal to H squared. That's the goal. That is the Pythagorean theorem. Right. I'm just going to call it Pythagorean theorem now. Even though, again, like I said, this was not something that was unique to the Greeks. Excuse me, I'm sorry. All right, so let's look at what's going on here. So forget about all of this diagram, and just in your mind, imagine I drew this right angle and then put H there. Okay, now what we do next is we then draw the square on H. Okay, so the diagram, I used a ruler to try to make everything look nice, but I messed up a few spots, so don't look too closely at it. But we start with this right triangle here, okay? This is the hypotenuse, and then we draw a square around it. Or we draw a square on the side of H. Okay, now what we want to do is we want to be able to do things like compare areas with known areas. So notice what happens here. If I have a triangle here, if I have a side length here, and I have the same side length there, I can kind of go the other way and draw the triangle from the hypotenuse. So I can start from the triangle and then go the square. Or if I have a hypotenuse, then I can give a right triangle. So of course, anytime you have a line, you can make a right triangle out of it. And this is what I'm doing here. So if you have, if this is the hypotenuse, and you want this to be the opposite angle, the opposite angle is the right triangle, the right angle, then this and this, you're fixed at what they are. Whatever the distance is, whatever the vertical distance is there, and the horizontal distance there. Anyways, this has to be A and that has to be B if you just think symmetrically. Okay, so then similarly, we're going to draw a triangle here and here, and the sides are color coded. So this side length is A, this length is A, this length is A, this length is A, and then all the purple lengths are B. So this is B, this is B, this is B, and this is B. Okay, so let's think about the area of the green rectangle. So the area of green rectangle Okay, what is the area of the green rectangle? Well, there's like 5 different regions. There are these 4 triangular regions here, and then this square. Okay, so again, let's think about this. What are the triangular regions going to be? What are the area of the triangular regions? Let's look at this one. Well, if we start with this rectangle, if we start with this triangle here, what we're going to do, again, start with this this triangle here. What we're going to do is we're going to extend a line or a line segment from this point here, the corner of the square, this way, and we're going to extend it a length of B. Okay, and then we're going to come down a length of A. In other words, what we've done, this triangle is the same as that triangle, or the area of that triangle is the same as the area of that triangle. We've just basically extended this to be a rectangle. So that's going to be 1. And of course, the area of this triangle is going to be 1/2. Well, H squared is obviously the area. But the area of this one triangle here is going to be 1/2 A times B, the area of this. Okay, now if you look at this triangle here, what we've done is we've extended a line segment this way, parallel with this line segment in the same length, and then this line segment as well is parallel with this line segment in the same length. So again, we've just taken this square, or taken this triangle, and have extended it to a rectangle. And so that's the area of that. That triangle there is going to be 1/2 AB. And similar things are true for these rectangles. So plus 1/2 AB plus 1/2 AB. Okay. So now all we have left is this area right there. The diagram kind of indicates that it's a positive area. Of course, we have to sort of say which is going to be the longer length. Is it going to be A or B here, and then kind of draw things appropriate there. But let's see what the side length of each of these sides are. I mean, it's not even clear to me at this point that side length is the same as that side length, or that side length is the same as that side length, or anything like that. So let's think about what the side length has to be. So this entire distance. So the distance from here to here is A, because A, because it's the rectangle there, and this distance there is A, and then this distance here is B. Okay, so in other words, what I'm saying is this length here is B, this length here is A, so this length here must be B minus A. So this side length here is B minus A. Okay, now what about over here? This length is B, this length is A, like I said just a minute ago. So then this length here has to be B minus A. And now similarly, this length is B, this length is A, so then this length is B minus A, and similar arguments say this length is B minus A. So then over here, we're going to add plus B minus A squared. Okay, now what's going to happen? We have 1/2 times AB. We have that written 4 times. So 1/2 times 4 is 2. So this is going to be this term. I'm going to switch it around to A minus B squared. B minus A squared is A minus B squared. And then plus 2AB. And of course, A minus B squared is equal to A squared plus B squared minus 2AB. And so this will simplify to A squared plus B squared. And there we have a proof of the Pythagorean theorem. So again, I want to just recap the order of drawing the diagram. We start by drawing this square here with hypotenuse. As soon as we have a hypotenuse or a length of any kind, we can draw a square based on that. Then, for example, if you look at this line right here, or this line segment right here, we can draw a right triangle such that the opposite angle is a right triangle. There's only one way to do that, and it's all well defined. We can do that here, here, and here. Then if we look at this example over here, we're going to extend this to a rectangle, extend this triangle to its kind of natural rectangle, the thing that you get, the 1/2 base times height area formula from. We're going to extend it to a rectangle and extend all these triangles to all of these triangles to a rectangle. And because of the way the diagram is, we know that they're not going to overlap each other. In other words, it's not like this this triangle is not going to encroach on this triangle, and so on and so forth, just based on this. Okay. Anyways, so that's it. That, like I said, is one proof of the Pythagorean theorem, which again is what I'm calling it, but it's probably not what Zhao Shuang called it. I like it. I think these picture proofs are nice. The book has kind of a more negative attitude and asks whether or not this would constitute a proof for us in modern times. And my answer is yes, I think it would constitute a proof. I don't really know why it wouldn't. I think the major criticism the book had is just something about not arguing whether or not something is a square. But okay, not every single claim in a proof is going to be spelled out explicitly. Some of it is just left to the reader to sort of reason on for themselves. But this is it, and I hope you liked it.